Okay, so here's a problem that we're trying to find the slope and displacement at point B, which is the free end. Okay, so we're going to use conjugate beam for that. So that requires us to draw the shear moment. So I'm going to go ahead and, without explicitly doing it with our equations of equilibrium, I'm going to find that the shear at A is 5 kips, and the moment at A is going to be 75 kip feet. I think if you took some time, another minute or two, you could easily draw a free body diagram and find those reactions. So from that, I'm going to draw the shear force and bending moment equation. So I'll create a template and include that center point underneath the load. So we'll start by drawing the shear diagram. I'll establish a positive x-axis, positive shear, and all of our shear values will be in kips. So starting at the left side, you can probably see that we have a positive shear of 5. There's no load, so the slope is 0. And you can see we have a constant shear over the first half of the beam of 5 kips. If I then draw the moment diagram, so I'll have a positive location for x and the moment, and kip feet for the unit. What's the initial moment at A? Well, it's 75, and that's negative. And of course, the change in shear is the area of the change in moment is the area of the shear diagram, and this area is positive and also equal to 75, so the moment goes to 0. It has a constant slope of the moment diagram because the shear is constant, and you get a curve that looks something like that. So there's my moment diagram. So let's come over here and draw the conjugate beam. So from our earlier discussion in class, we should know that a fixed connection in the conjugate space is free, and a free end in the conjugate beam is fixed. So we now have a structure that looks something like that. So there's our conjugate beam. Now what's the load on the conjugate beam? It's the M divided by what? EI. So this is all negative, right? All negative moment. So that means negative, if we translate it as a force, negative force is up or down for us? Down. So I'm going to say, okay, it's 75 there. And it goes to 0 here, so my distribution looks something like that. And this will have a value of 75 over EI. And this distance is 15 feet, and this distance is 15 feet. Now this problem says, what is the slope and displacement at B? And B is here. So slope and displacement in the conjugate beam is shear and moment. So the shear and moment at B is, interestingly enough, just the reactions. So I just have to solve this problem for the reactions at B. Can you do that? I think you can. So I'm going to come over here and say, well, here's my positive moment at B, and here's my positive shear at B. I can come back and get my concentrated equivalent force. It's not much room there, so I'll just call it F. And then I'll come down here and write that F is what? Well, it's a triangle, so it should be 1/2 the base, and the base is 15, and then the height, which is 75, and that's kip feet divided by EI. So what's that? The force is good. What's that force going to be?
562.5.
562.5, and that's going to be kip feet squared, and then you'll divide that by EI. We've talked about this before in class. We know the units of E and I are also force length squared. So once you get this worked out, this term should really be dimensionless. Now, what's the distance from the force to here?
25.
Yeah, so if you break it apart here, we know this part is 15, and this part to the center of the triangle is 2/3 the distance, and 2/3 of 15 is 10. So that should give us all we need to take this free body and find the moment. So we'll start by summing the moments at B. Make sure it's in equilibrium. So starting at B, I have the moment, which is right-hand rule would be positive moment. And in this force, positive or negative moment about B? Don't be shy. Positive. So the force is 562.5 kip feet squared over EI times a moment arm of 25 feet. So it looks like my moment at B, which is really my displacement at B, is equal to what? It looks like negative 562.5 times 25, which is
14,062.5.
14,052.52? And that will be kip feet cubed over EI. Well, in this problem, EI is 30,000 KSI and 1,800 inches to the fourth. So let's figure out what that is. So the displacement at B is going to be minus 14,062.5 kip feet cubed. I like to do this. You guys may have seen this technique before. I think it helps you keep up with the units. So there's the first term, and then E becomes 30,000 kips per square inch, so the square inch comes up like that. And then the I term is 800 inches to the fourth. And then the last term is what? It's a conversion term, right? Since I've got inches and feet, let's do it in inches. So let's get rid of the cubic feet. So we know that there's 12 cubic inches in 1 cubic foot. Okay? So you can see the kips cancel, cubic feet cancel. I've got inches to the fifth divided by inches to the fourth, which is inches, so that's good. So what does that number turn out to be? It's going to be negative 1.01 is good enough for me. About 1 inch. And now if I come back and I sum my forces in the y direction, I'll assume up is positive. So let's see what we've got. We've got our shear at B acting down, VB, and our load is also acting down, which would be our 562.5 kip feet squared over EI. Solve for the shear. So the shear at B, which really maps to the slope at B, is equal to minus 562.5 kip feet. Oh, I got cubed. I meant square. Sorry. Divided by EI. So since we have values of EI, we can go ahead and calculate that. So I'll have my minus 562.5 kip feet squared. I'll draw my line to help me keep track of all my units. So again, I'll divide that by 30,000 kips per inch squared and 800 inches to the fourth. And I'll have my same conversion as the previous one. 12 inches cubed is a foot cubed. And what do I get? Now let's look at what happens here. I've got kip cancels. I did something wrong here. Oh, I did this wrong. This is squared. Sorry. So this part in the numerator will be 12 squared, which is 144. So now my feet squared cancels. So I have inches squared twice, inches to the fourth, inches to the fourth. All the units cancel. So I have a dimensionless number, which is, I think, going to be pretty small. Anybody calculate that? 0.0034. And that will be in radians. Pretty small angle. It's so small I can't get my thing in there there it goes. This should be phi at B. Not. It kind of makes sense too. When this beam displaces, it's probably going to do something like this. So you can see I've got a negative displacement and my slope is also negative. So at least the signs match up. So any questions about that? All right.